So where we left off before was really trying to understand the sampling distribution of sample means, which is if we were to take an infinite number of samples from a population and look at, say, the mean age from an infinite number of samples, graph all those mean ages, we would get a perfect normal curve. We would get a sampling distribution of all of the sample means. And that normal curve we could chop up and have the percentages being within 2 standard deviations, or really 1.96, would be 95% of all the means would be within 2 standard deviations, and 99% of all the means would be within basically 3 standard deviations, or more specifically 2.58 standard deviations, or z-scores as we also call them, okay? And these are those cutoff numbers that I really need you to memorize. The examples that we looked at average income for a community and how if you took a sample, so if you look back at those notes, those slides from that, I just want to revisit that for a bit. If you took a sample of 500 people from a community, we don't know the income in the whole community, but we have a sample, and we know that the mean income is $45,000 just in that sample. We know that the standard deviation is $200, so the average variation from the mean is $200. And then what we really want to know is how can we create an interval around this 45,000 in which we can be pretty confident that the true population mean exists. So we learned how to create these confidence intervals. We have to make a decision about how confident we want to be. And we really have 2 levels that we're choosing from. 95% confident or 99% confident. 95% confident, we'll see how it changes if we do 95 versus 99. But when we say we're 95% confident, that means we're setting what we call an alpha level of 0.05, which means we're leaving 5% up to chance. And this corresponds to our standard deviation score, or z-score, of 1.96. So that's where we get that from. And then in order to create the interval, we have this formula, basically, that starts with our mean of 45,000, and then we say plus or minus because we're going to add and subtract from that. And we're going to use 1.96 as our z-score. And then we're going to multiply that basically by our standard deviation measure, which is the 200 divided by the square root of our sample size minus 1. So it's the square root of 499. When we do all that math, what we found was we had basically a confidence interval in which we would be adding and subtracting. So we do all that math, you end up with $17.55, which when you create an interval, so you add that, you would obviously get $45,000 and $17.55. And on the other end, you would get $44,000, $982.50. What this gives us is a range basically of only $35. That's our range. That's our confidence interval. So what we're saying here is we can be 95% confident that the true mean income in the population is somewhere between $44,982 and $45,017. This is what this is telling us. So I gave you a couple of other scenarios so that you can understand what happens if we change our confidence interval to 99%. The only thing that changes in the math is this. So instead of 1.96, if we want to be 99% confident, because we want to be more confident, we're going to multiply this times 2.58. And then this becomes what? Larger or smaller, do you think? It becomes larger, becomes 23.09, which changes our range when we do our math to 44,972 245.76 to 45.023. Now, just so you're aware, so this was our 0.05 level. We had a range of $35. This range at the 0.01 confidence level is actually $47. It's wider. The reason it's wider is because when what we gained in confidence, we lack in precision, or we lose in precision. So even though we were less confident when we had this other range, we were more precise. Not by a whole lot, but we had sort of a more narrow range. So that's an important concept to understand. Another situation we looked at is, what if we had a smaller sample size? So this time, let's just go back to that 1.96 confidence level. We're going to keep our confidence level at the 95% level. But our sample size, we're going to now change to 100. What happens then? So now we have the square root of 99 instead of 499. What happens when we go from 500 people in our sample to 100 people? What we see is that this number is actually even wider now, which gives us now a range of, it's not worth really writing these out because you don't really, what you really care is the actual range, but I will do it just to do it. Now we have an n equals 100, which is much smaller, and our range is actually $79. So we now have less precision simply because, are you trying to tell me to stop? Okay. We now have less precision simply because we have a smaller sample size. So you can flip that too. The larger sample size we can get, we're going to have a more precise, a more narrow confidence interval. Likewise, the smaller sample size, we're going to end up with a wider confidence interval. Let's look at one more scenario. Let's look if we have, let's go back to 500 people. We're going to keep it at 1.96, but this time, and we're going to go back to our large sample size. Yes, so 499. But this time, we're going to have a much, much larger standard deviation. So this time, our standard deviation is actually going to be $100,000, which what this is actually closer to reality, because in the United States, we have a very large standard deviation of income. So we have, a few people who make millions and millions of dollars, billions and trillions of dollars, and then we have a lot of people at the way other end, and then a bunch of people in the middle. So it's well spread out. So this is actually closer to reality, in fact. So what happens when we have a standard deviation that's much, much bigger? What happens to our confidence interval? So we're going to put 100,000 up here. And guess what? It's really, really large. It becomes, 8,773.51, which actually I'm not going to write out the whole range, but it ends up with an interval of 17,000. The range, we'll see, our standard deviation is $100,000. Then our range is actually going to be $17,547 range. So we went from a $35 range in a confidence interval to a $17,000 range, all because we had a much, much greater standard deviation. So those are three things that I want you to understand impact this confidence interval and creating it. The level of confidence, whether it's 0.05 or 0.01, 95% or 99%, the sample size, and the standard deviation. So those are three concepts, or three questions that I have posed that I want you to be able to answer. All right, let's go over just one of the homework problems, and then I will post the other two, well, I'll post all of them online for you, but I'm just going to go over one of them. Okay, so let's go over the first one. The first one was question 6.4. And it has, you've developed a series of questions to measure job satisfaction of bus drivers in New York City. Of course, you don't have access to all of those bus drivers, so you just can get a sample of 100 bus drivers. So you have a sample of n equals 100. You have what other information you need? You need what is the mean level of job satisfaction. So assuming you surveyed these people and you found out that they have a mean job level of job satisfaction of 10.6. So when you figure out a problem like this, just write down those mean pieces of information. The standard deviation was 2.8. And then the last thing is, what is the level of confidence for which we're going to make a confidence interval? And they say use the 95% confidence interval, which means our alpha is 0.05, which means basically that z is 1.96. So we're going to work from our formula, starting with our mean, which is 10.6, plus or minus, and then in parentheses, oops, first we need our z-score, because we need to know how many standard deviation units are we going to create around this interval. It's going to be 1.96. And then our standard deviation is 2.8 divided by square root of our sample size minus 1, which is square root of 99. So when we do our math, I'll just walk through this. It's 10.6 plus or minus 1.96. You'll end up with 0.28 here. Then if you multiply those, you'll end up with 0.55. Then I'm going to take 10.6, I'm going to add 0.55 to give me 11.15. And then I'm going to take my 10.6 and subtract 0.55 to give me 10.05. So this is where my range is going to come from, my confidence interval. Confidence interval now equals 10.05 to 11.15. What do I say is my sort of concluding paragraph? So you say I am 95% confident, make sure you're saying whether 95 or 99, that a true population mean of job satisfaction.
You can write farther.
I can?
Yeah.
Okay. Of job satisfaction among who? Among New York City bus drivers is between 10.5 and 11.15. That's it. That's what I expect in terms of an interpretation. Okay, so we did this based on what we knew about the sample and what we know about the sampling distribution of sample means. So it's a powerful, what? Okay, my son is saying go faster. All right, so it's a powerful concept. Let's apply it in another way. Let's move on to what our real lesson is for today, which is how do we apply this concept to actually estimating or to comparing a sample mean to a population mean. So we're kind of doing that in this way, but we're going to take it a step further. I'm going to erase this. Don't pause it, keep it on, because I don't want to have to put those together. So this is what I would normally do in class. Okay. Oh, you know what I wanted to say? I want to add one thing. Sorry. I think it's worth putting the screen back up. I know. One thing is worth pointing out to you is so we have it, let's say you have a sample mean that, here, you're creating a confidence interval around that sample mean. So that could be, say, your 95% confidence interval. This would be your 99% confidence interval, but your sample mean, when you create that interval, is only so far from the true population mean. So it's trapping it, it's capturing it within the interval. Now, it's certainly possible I could have gotten a sample mean that was kind of, crazy out here, where it would be very rare because it's all the way out here. So then when I created a confidence interval around that, I might have missed trapping that population mean, because that rare instance where I got my sample was actually a rare value. But again, the emphasis here is on rare. So when I created that confidence interval, maybe I missed it with the 95%, but maybe I got it with the 99%. So I just wanted to kind of show you that overlay of when you're creating those confidence intervals, it really is a reflection of how far that sample mean is from whatever the true population mean is, which we don't quite know. We don't know. But based on our theory, we know that our sample mean 95% of the time and 99% of the time are going to be pretty darn close to the true mean. That. Okay. All right, so look at your slides, look at your reflection questions, which are available to you. And I'm going to go through these. Yeah, we're still really talking in some theoretical terms, and we'll start to apply it by the end of this hour. And ultimately then, for the rest of the semester, we'll be using the same sort of logic and steps that I'm introducing today. So it may feel esoteric. Look that word up. My kid's vocab word for last week. It may feel esoteric, but that's okay. It's supposed to. It's theoretical. It's something I want you to try to grasp and apply. And we certainly will be applying it throughout the rest of the semester. So hypothesis testing is where we really are starting out with a research question and a hypothesis and testing it. So let's start with a research question that's based on the question or the issue of the media, let's say, is reporting that the elderly are victimized by crime more often than the general population. So how do we test that scientifically? One way we can do it.
Memory.
How much memory is there?
A little bit, so go faster.
Okay. So one way we can test that, we can ask the research question, is there a difference in how often elderly people are victimized by crime compared with the rest of the population? That's a research question. We know how to create those. The hypothesis that we would have, a non-directional hypothesis, would be there is a difference. Or sometimes we say there is a relationship, but there is a difference in how often elderly people are victimized by crime compared with the rest of the population. So we're going to be really talking about sort of like this elderly group of the population and the whole population. So kind of like two populations, like a subset. So we're not really going to talk about this in terms of a sample right now, just thinking about, you have a community and you want to compare the elderly with everybody else. The first step that we need to take is deciding what are the underlying assumptions that guide our statistical work. The first is that we do random, well, like I just said, we're not doing sampling, but if we were sampling, it would be random sampling. But also important is to be able to say what is the level of measurement of whatever we're measuring, because that will go along with whatever statistical test that we ultimately choose. So this isn't that important with what we're doing right now, but it will become more important later. Number of times somebody's been victimized, that is an interval level variable. You know, it's a number. I've either been victimized once or twice or 0. So that's an interval level of measurement. Okay. The second step is some new language possibly for you. And that's where we want to state a hypothesis. But we're going to have two types of hypotheses. One is what we call a null hypothesis, and one is what we call an alternative hypothesis. The null hypothesis is a statement that there is no difference. There is no relationship. So we always want to begin with the assumption that the null hypothesis is true. So it's like a negative hypothesis in a way, a null hypothesis. And there's a symbol of HO that we look at and know what that means. That's the null hypothesis symbol. And then your goal is to see if you have enough evidence to conclude that another hypothesis might be true. Or is it, you know, that the null hypothesis is not likely to be true. So the other hypothesis that there actually is a relationship, we call that the alternative, or sometimes we call it the research hypothesis. And we denote that with H1. So it's either null or alternative, HO or H1. That's pretty straightforward. The metaphoric example that Dr. Harris likes to give, and I like too, but it's as if you have a criminal trial where you have a jury, and the jury's null hypothesis is the defendant is innocent. They have to start with that. That's their job, okay? And is there enough evidence to prove that they're guilty, which is the alternative hypothesis, the research hypothesis. So if the jury doesn't know which one is true, they must make a decision based on the evidence presented. So keep that metaphor in your mind. I'll come back to that. All right, so there again, the null hypothesis. There's no difference in how often the elderly are victims of crime compared to, you can compare them to anybody, but we're saying the general population. And I'm also stipulating, it's probably a good idea to say, you know, how, per year are we talking about, per month, what are we talking about? So we say per year. And then what we're saying also, just another way of symbolizing what we're saying here, is that the mean amount of victimization among the elderly, so we're going to call that mean mu1. So that group, mu1, is going to be equal to the amount of victimization for the general population, which is mu0. So we're just going to have a different symbol for each. So, and then obviously when we're saying the alternative hypothesis, we're saying mu1 is not equal to mu2. I mean mu0. So as soon as there is a difference. I'm saying the same thing over again. Well, the only difference here is mu1 not equal to mu0. So here's our summary. Okay. So you got to do that. All right. Then we get into what we call significance testing. So the question is, wait a second, let me just make sure something here. I didn't want to go there. Okay. Oh, I know what I want to show you. Okay, so there's some other language I want you to know. So in statistical language, we say when we, basically when we, say we conclude that there is a difference. Say we could make that conclusion. We collect evidence, we collect data, we decide, ooh, there is a difference between these two populations. But the reality is there really is not a difference. In other words, maybe we looked at our evidence incorrectly, maybe our sample was weird the way we collected it. So really we made a mistake. So we've said there's a difference when there's not. That's what we call a type 1 error. And the metaphoric example to that is like when the jury convicts somebody who's innocent. So the jury decides, we have enough evidence, okay, yeah, you're guilty. But then they end up convicting somebody who's not guilty. They've committed a type 1 error in statistical world. That would be a type 1 error. And actually, when it comes right down to it, we're calling that alpha level the probability of a type 1 error. So we want that probability to be really small because, you know, in the world of criminal justice, you don't want to convict somebody unfairly, right? The opposite of that is a type 2 error, and that's where you determine, oh, no, the elderly aren't victimized any more than the general population. There's no difference there. But there is a difference, and you just missed it. For whatever reason, you missed it as a researcher. That's called a type 2 error. And by the way, when you decide there is a difference, you are rejecting the null hypothesis. That's the phrase that you might use. You're rejecting the null hypothesis. When you commit a type 2 error, you're failing to reject, get this one, you're failing to reject a false null hypothesis. So in the metaphor world, it occurs when somebody's really guilty and you acquit them. So that's not a good thing either. These two probabilities are actually inversely related. So if you decrease the probability of one, you're increasing the probability of the other. And typically, this is a more serious error because when you think about it, if you don't determine when there's a difference, and there is a difference, then you might be missing some really important data that could help people ultimately. So we call this the probability of a type 2 error is called a beta error. So we'll come back to using that terminology over and over again. So I'm just introducing it here as it relates to hypothesis testing. Type 1, type 2 error. The book does a really nice job describing that as well. But it really relates back to what you do when you have your data and when you make your decisions and when you make your conclusions, how accurate are you being? And what is the probability that you're going to make those mistakes? Because there's always a chance you will. All right, so that was all part of step 2, which was establishing your hypotheses. Step 3 is, this is basically what we were doing when we were coming up with confidence intervals, is we're saying how confident do we want to be that we're going to make an error or not. So again, we're deciding whether we want to be 95% confident or 99% confident. So really, we're just deciding one of those two things. So we're going to think about that normal curve again. We're going to think about those two sort of cutoff points, either 1.96 or 2.58, which is further out. And we're going to call that point that we choose our critical value. So in a minute, we'll get into an example of this, but really we want that sample mean to fall. If our critical value is 1.96, we really want our sample mean to be within this range of the true population mean. And if it's not, then we would have to conclude, that there's actually, the population. So, for example, if our elderly population, if the victimization rate was within this range, and the general population's victimization rate was here, then we would conclude that it's close enough. There's no difference. It's totally within the realm of possibility that the elderly group has a victimization rate similar enough to the general population. Now, if we had a sample where the elderly rate, the victimization rate, was this far away on either side, because we're not saying it's higher or lower necessarily, we're just saying it's different, then we can definitively say it's outside the realm of our confidence here. I mean, we're basically saying it's outside of this critical cutoff point. So thus it would be a rare occurrence for it to exist by chance. And it is significantly different from the general population mean, which is right here. So that's the logic of what we're doing when we're... Okay, one more thing to point out about this, and kind of going back a little bit here. So if you have a group of the elderly people that you're looking at their victimization numbers, and you're comparing that to the general population, and you find that the number of times that elderly people have been victimized it actually is this far away from the mean in terms of standard deviations. No, let's say it's over here, this far away, either way, in this blue area. Then this is what we call, it's in the region of rejection. So the mean that you got with the elderly folks was actually, far enough from the mean in the population, and so that it falls into your region of rejection. We call it the region of rejection because it's the region in which you reject the null hypothesis, which, if you remember, is that there is no difference between the elderly and the general population. So, all right, I wanted to make that point. And so, again, when we're talking about this right now, we're basically saying that it's possible, the way we're testing this out, that this mean value with the elderly group could be either less than or greater than. We're just saying it'll be different. And we can test that in a region of rejection starting at 1.96 or at 2.58. Now, if we do it at 2.58, it would have to be even more different, so we're being more stringent, basically, because we're saying, it'd have to be even further away from the population mean in order to reject our null hypothesis. And 0.001 even further still. And if you remember when I said last time about, the 0.001 levels of confidence, basically, you use that a lot with medical research, when you're really wanting to be absolutely sure that the patients who took this drug got significantly better than the other patients. You want that amount of better to be so different that you need it to be this far away from what the general population is before you start selling this drug and saying it works. Okay, so what we do really, we have to figure out, back to this picture real quick, we have to figure out with the elderly group, with that mean, we have to put it on the scale somewhere, so we have to figure out kind of what is the z-score for that mean, basically. Is it greater or less than 1.96? Because if it's greater than 1.96, then we can reject our null hypothesis. But we have to put that into basically a z-score formula, like we did with your school, scores on your exams, in order to determine that. So we call it our z obtained because it's obtained from, whether it's a sample that we collected or in this case our group of elderly people. But basically, all we're doing is we're subtracting the mean difference from of one group from the other, and we're looking at what the difference is, and then we're dividing it by our measure of standard deviation, which is, if you look back up there to the z-score, that's what we did to figure out what is the z-score. So if we look at this as an example again, this was our null hypothesis, our research hypothesis, and let's look at this example with real data here. So we're going to set an alpha level of 0.05, so not too strict. We have a sample size of we have 127 elderly people in this community, and we don't need to know the number in the general population. We just need to know the number in that smaller group that we're comparing. We have our two means. So these are the number of times people have been victims of crime in the last year, on average. So in the general population, it's 1.2 times. Among elderly people, it's 1.6 times. And then the standard deviation for the population is 1.43. That's for the elderly group. So if you look at the right top, that's our formula, and we're just going to plug in our numbers. So it doesn't really matter what numbers you subtract from which in terms of the means. because it doesn't matter if it's negative or positive in the end, because we just care how far away it is from the mean of the general population. What's the difference? So when we do all that math, we end up with basically a z-score of 3.15. What does that mean? What it means is when we, can you see under here, Calvin?
Nope.
Down here?
Mm-mm.
Okay.
No.
Can you?
I said no.
Huh?
I said no.
All right. Can you adjust it for a second for me? So what does that 3.15 mean? Again, when we look at our, remembering we set a cutoff or a critical value of 1.96. So if you think about the mean of the general population in terms of 1.2 times that they were victimized by crime in the last year, and then the elderly population, how many standard deviations away from 1.2 were they? And it turns out they were 3.15 standard deviations away. So they were actually way over here. Way far away, so this is corresponding to a mean of 1.6. So that was their mean. That was U1, this was U0. But in terms of z-scores, 3.15 standard deviations away from the population, in the general population. Which means this is in the region of rejection. It's larger than the value of 1.96, it's over here. Which means what? It means we can reject the null hypothesis that there's no difference. Okay, back up please, Calvin. Last minute or two. So we have to interpret our results. And I just did out loud for you. We have a couple of decisions. We have one decision to make. Do we reject the null hypothesis or do we fail to reject the null hypothesis? We never accept it. We never use the words we accept the null hypothesis. We either reject it or we fail to reject it. If the test statistic, that's the one we just calculated, our z-score basically, if it's in this critical region, either plus or minus, then we reject the null hypothesis. We are saying that there is a significant difference between our elderly group and the general population. We are saying the difference is statistically significant. If that score was not greater than 1.96, if it was somewhere here or here, then it would be close enough to the general population that we would fail to reject the null hypothesis. That we would decide there's no significant difference between the general population and the elderly population in terms of how often they are victims of crime. So, let me give you, okay. So I just said that. That's what I just said. Let me just show you one more thing, last thing, interpretive paragraph. This is what I want you to include when you're doing an exercise like this. And we will do many more examples of this on Tuesday, or at least one or two more anyway. But these steps that we're taking are the same steps we're going to take for all of the statistical tests we're going to be doing over the remainder of the semester. So you will get the practice of these steps. They're basically the same. We just might do different math each time. But when comparing a population of elderly people, n equals 127, with the general population, elderly people are victims of crime significantly more often than the general population. And I'm going to give my z-score, z equals 3.15, and I'm going to give what we call my p-value, meaning the probability that I'm wrong with this. But you see this in your research readings all the time. P, and I'm going to say less than or equal to 0.05. That's how we write it. In a given year, this is my final sentence, which in a given year, elderly people were victims of crime an average of 1.6 times, while the general population were victims of crime 1.2 times. So what you've noticed in that paragraph are these important 4 points. One, I'm describing both groups I'm comparing, and I'm including the N with the information that I have for the elderly group. I'm being very specific in what variable was compared. So how often they were victims of crime, and I should have said, yeah, in the last year. I'm providing the means for the variables for each group. So what was the mean for the elderly group? What was the mean for the general population? And I'm making sure I provide what the Z obtained was, the Z-score, and what was my alpha level, the p-value. That's what you need to include in an interpretive sentence when you're doing this kind of hypothesis testing. Let me just make sure if that's it. So that's all I'm going to cover today. Please, please watch this again and again. Use other, I'll try to see if I can put up some other videos you can look at as well. Please use your books. That's what they're there for as an additional tool. I'll see you Tuesday.